Hello, today we're going to be covering some advanced topics on complex numbers, specifically 3 topics: how to simplify higher powers of I, the complex conjugate and dividing complex numbers, as well as how to plot complex numbers and find their absolute value. So the first thing to remember is that a complex number is of the form a plus bi. A is your real part, bi is your imaginary part. In order to simplify higher powers of I, we're going to call upon 2 properties of exponents that I'm going to utilize. Specifically, a base to a power times the same base to another power. What I do with those powers is I add them. And the other one is when I have a base to a power raised to another power, I multiply those. Okay, just a couple things to remember. All right, so the definition of I says I is the square root of -1. When we're trying to write this in standard form, we just write that as I. Now, I squared then would be -1. I cubed I can simplify or reduce to I squared times I to the first. That's using this first property of exponents. Well, we know I squared is -1, and I, we just refer to I, so I cubed is -I. I to the 4th is the same thing as I squared times I squared. Remember, I squared is -1. So this is like -1 times -1, which means this is just 1. So this is the first 4 powers. Now, we really need to know these first 4 because look at what happens when we go a little bit higher. I to the 5th can be written as I to the 4th times I, but I to the 4th is just 1. So I to the 5th is I. I to the 6th is the same thing as I to the 4th times I squared. I to the 4th is 1. I squared is -1. So this just gives me -1. I to the 7th is the same thing as I to the 4th times I cubed. We know I to the 4th is 1, and I cubed is -I. And I to the 8th, well, that's just I to the 4th times I to the 4th, which means it's 1 times 1, or 1. So notice that this pattern keeps repeating. I, -1, -I, +1. I, -1, -I, +1. So the key to simplifying these is always to figure out how many I to the 4ths you can pull out of any number. So let's go ahead and take a look at a couple examples. Okay? So the first example that I want to look at right now is this, I to the 54th. So I need to know how many I to the 4ths I can pull out of here. So the big thing is let's divide 4 into 54. This goes in once, that goes in 3 times, and we have a remainder of 2. That means I can write I to the 54th as I to the 4th to the 13th times I squared. Now think about that really quick. I to the 4th to the 13th. This part is really I to the 52nd times I squared. That gives me I to the 54th. We're used to going this way, okay? And again, I was looking for how many I to the 4ths I could get, and I was able to get 13 of those. And then I did have a remainder of 2, which is my I squared. Now, why I like writing it in this form? Well, now I can simplify this. So I to the 4th to the 13th times I squared. Well, I to the 4th is just 1. So 1 to the 13th times I squared, well, that's -1. So this equals -1. I to the 54th is equal to -1. Okay? Now we use a lot of detail for that one. Let's try another one. Okay. Here's our next one. I wanted to find what I to the 129th is. So again, I need to find out how many I to the 4ths I can get into there. So this is 3 and 12, 9, 2, gives me 8, remainder 1. All right, So that means I to the fourths, I get 32 of them, and I have a remainder of 1, so that's I to the first. I to the fourth is 1, I to the first is just I, so I to the 129th is the same thing as I. Okay. All right, let's look at another one. Our next one. Let's go down just a little bit here. Our next one is I to the 435th. I to the 435th power. Again, how many times can I get I to the fourth out of there? It's in 1, gives me 4, 3, doesn't go in at all. Bring my 5 down. This goes 8. Yes, I had to think there. So 32, remainder 3. All right, so I to the 435th is I to the fourth, 108 times my remainder, which is I cubed. I to the fourths become 1. We know I cubed is I squared times I, which is -1 times I. So I to the 435 is -I. Done. All right. One last one. Let's do I to the 268th power. Again, I need to see how many I to the fourths I can put into 268. All right, so this goes 6, which gives me 24, 28, that goes 7, and that leaves me with a remainder of 0. Okay, so let's think about this. This means I have I to the fourth, I have exactly 67 of them. That is what is equal to I to the 268. Well, I to the fourth is just 1, and 1 to the 67th is just 1. Now, if you need to, I to the 0, think about anything to the 0 power is always 1. Anyway, hopefully you found that helpful. Let's go ahead and move on to our next topic, and that is the complex conjugate and dividing by complex numbers. Okay? All right, so if you're given any complex number in standard form, its complex conjugate looks like this. The only thing we're doing is changing the sign of the imaginary part. So, if my number is 3 plus 2i, the complex conjugate is 3 minus 2i. If I have 5 minus 4i, its complex conjugate is 5 minus 4i. If I have 1 plus I, its complex conjugate is 1 minus I. So now here's the question, and this is what's going to help us with division. What do we get when we multiply a complex number by its conjugate? So let's just take a look at this first one. If I take 3 plus 2i and I multiply it by 3 minus 2i, you may recognize that this is something you have to distribute or double distribute or FOIL. So let's do this. 3 times 3 gives me 9. 3 times negative 2i gives me negative 6i. 2i times 6 gives me plus 6i. And 2i times negative 2i gives me negative 4i squared. Well, my negative 6i and my positive 6i canceled. So I get 9 minus 4i squared. But we know that I squared is negative 1. So that means I get 9 plus 4, or 13. This is what's great about multiplying a complex number by its conjugate. What you end up getting is a real number. So what that does is it helps us divide complex numbers. So let's go ahead and take a look at a couple problems. So the first problem I have is 4 plus 2i divided by 1 plus I. So this is a division. In order to divide, I basically want to get rid of the complex number in the denominator. And I'm going to write this in standard form. So what I'm going to do is I'm going to multiply both the top and the bottom of my fraction by the complex conjugate of the denominator. That will make it so that I have a real number in the denominator. So I'm going to have to double distribute here for the numerator and double distribute or FOIL for the denominator. So let's go ahead and do that. So this is going to give me 4 minus 4i plus 2i minus 2i squared. That's my distribution in the numerator. In the denominator, 1 minus I plus I minus I squared. Okay, let's keep going. So I've got a couple like terms in the numerator, but I also know that this I squared here is -1. Same thing in the denominator. I've got some things that canceled, and so I have 1 minus I squared, but again, I squared is -1. Okay, so this becomes 4 plus 2. Then I have my minus 2i, and in the denominator I get 1 plus 1, which gives me 2. Now I can simplify this even more. 6 over 2 is 3, minus 2 over 2 is I. So that very complex looking number is now simplified into standard form. All right, let's look at one more. This next one is 5 divided by 2 minus 3i. Again, we don't like to divide by complex numbers. So we're going to turn this into standard form by multiplying by the complex conjugate of my denominator, which is 2 plus 3i over 2 plus 3i. Remember, any number divided by itself is just 1. So I'm basically multiplying this fraction by 1. Now in the numerator, I just have a simple distribution. So this becomes 10 plus 15i. The denominator down here, look at what happens when I multiply this all together. 2 times 2 is 4. 2 times 3i. Then I'm going to take my -3 times 2. And my -3i times positive 3i. Those two cancel, and I'm left with 4 minus 9i squared. But remember, I squared here is -1. So this becomes 4 plus 9, or 13. Now, to write the final answer in standard form, this becomes 10 over 13 plus 15 over 13i. All right, last topic now. The last topic is plotting complex numbers and finding their absolute value. So a couple things that you should know about this. 1, it's very simple. And 2, finding absolute value is just finding the difference from 0. So let's write these couple things down. So plotting a complex number like 2 plus 3i is like plotting the ordered pair 2, 3. Here's what I mean. Notice over here, the x-axis is replaced with the real part, and the y-axis is replaced with the imaginary. So since I have a positive 2, I go over to the 2 on the real, and I have a positive 3i, I go up 3, and there's my point. That is the number, I can get it, 2 plus 3i. Okay? All right, the second thing you need to know is the absolute value of a complex number. Is the distance to 0. So in this case, we're finding the distance between this complex number and the origin. So I need to know this distance right here. This is the absolute value of 2 plus 3i. Now, if you take a look, that distance there, or that absolute value that we have, is made up of two sides of a right triangle. This side, which measures 2, and this side, which measures 3. So that side has to be the square root of 2 squared plus 3 squared. Remember your Pythagorean theorem. So this is the square root of 2 squared plus 3 squared, which means it's the square root of 4 plus 9, or 13. Okay. So, in general, you're plotting an ordered pair for your A plus BI, and then you're just using the Pythagorean theorem to find your absolute value. So let's go ahead and let's take a look at a few more examples. Okay. All right. So if I wanted to plot the number, let's say -1 plus 5i. So I'm going to go -1 on the reals and +5 on the imaginaries. There's my number. Okay. And if I want to find the absolute value of that number, it is the square root of -1 squared plus 5 squared. That gives me the square root of 26. All right, let's try another one. So if I have 2 minus 6i, I'm going to go +2 on the real, -6 on the imaginary. I end up here. This distance here, that is the absolute value. So the absolute value of 2 minus 6i is the square root of 2 squared plus -6 squared, which gives me 4 plus 36, the square root of 40. And like usual, we do need to simplify this, so this becomes 2 root 10. All right, let's look at just a couple more. So now, here's what I want to look at. What if I wanted to plot -5i? Well, that has no real part. It's the same thing as plotting 0 minus 5i. Okay? So it's all imaginary, and it's going to end up right down here. And this is very easy because the absolute value of -5i would just be 5. It's the distance we are to 0, or the origin. Likewise, if I wanted to plot just the value, say -3, that's a whole real number. And that goes on the real axis and is right there. And its distance is simply 3. So the absolute value of -3 is 3. And that should look familiar. Anyway, that's the end of our advanced topics. Hope you enjoy.